Many of us have experienced already waiting in the lines, like when you go to the malls and pay to the cashier, or when you go to the bank and wait to be served, or when it's first day of school and you go to the enrollment process, or if you want to order your favorite McDonald's value meal, that BFF fries or a la king, sometimes or oftentimes it annoys us waiting in the lines for hours, and then you just can't help but think, what if there is another way of resolving this problem? Why can't the management think of something to reduce these waiting lines? People are just tired of this waiting in the lines, queuing for minutes, for hours. And anyway, in this video we will discuss about queuing theory and analysis for single server. If you're ready, let's start. So in general, we do not like to wait. But reduction of the waiting time usually requires extra investments. To decide whether or not to invest, it is important to know the effect of the investment on the waiting time. So we need models and techniques to analyze these situations. So in our real world, we experience having to line up to fall in line to pay to the cashier if you go to the university, or if you want to secure diplomas or your records from the registrar, or if you go to the banks and then you have to wait for your number to be served, or when you go to McDonald's to order your favorite chicken or fries, BFF fries, or when there is a traffic. We really hate traffic when there's traffic jam. And then in almost every entrance anywhere, in the malls, university, or wherever, there is a need to fall in line, especially when Christmas is fast approaching, and it is expected in the Philippines that our malls would be really packed those days. It's really annoying to buy groceries during those days before Christmas or before New Year, because you already know what is going to happen in the malls, in the cashiers. The lines would be very just horrific. Okay, so we don't want to wait. Basically, in general, we hate waiting in the line. It just stresses out everyone. And also in a concert, if you want to buy ticket for your favorite Blackpink or Taylor Swift or whoever you're fun with, or in the giving of government subsidies, 4 Ps every 14th day and 29th day or 30th day of the month, people are lining up in land bank and then to claim for their subsidies, allowances, and there is no more social distancing. It's quite ironic because we want them to observe social distancing, but these people can just help or wait for their turn. They really had to fall in line to line up. And anyway, in terminals and in almost all transactions in our lives, we always experience have to fall in line. Alright, so and that's really something exhausting to imagine. Anyway, so what is a queue? A queue is a line or sequence of people, vehicles, data, activities, or anything waiting their turn to be attended to or to proceed. For example, your midterm examination is fast approaching and there is a pile of documents, books, notebooks waiting for you to read. Okay, or there is a lot of quizzes, assessments in your LMS waiting for you to answer. Anything that is waiting in the line to be attended into is considered as a queue. So what is queuing theory? Queuing theory is a study of waiting lines. It plays a big role in solving and preventing operational bottlenecks and service failures in the organization. So since the history of man, we really want to reduce the waiting lines. We want to serve best our customers. We don't want them to wait. If we are part of the management, we don't want our customers to wait to be served. Okay, so this bottlenecks, this operational bottlenecks or something that have caused delays in the operation or have caused delays in the service, then that should be attended to. That should be resolved to reduce the queue. Let's think about it this way. So, your midterm is fast approaching, and there is a pile of documents, books that need to be read or done. And then something just came along. Your friends invite you to go to a party. That is actually a bottleneck if you say yes. Because after the party, you have to attend those things, and there will be limited time to read all of those. So you cram. So to reduce the bottleneck, to reduce the waiting time, to maximize your time, you need to remove the bottleneck. Meaning you must say no to the invitation, right? Because if you go to a party while your books, your notes are still waiting to be read, to be done, you know that you will need more time. You have to double your time once you get back home, right? Meanwhile, queuing analysis means a probabilistic form of analysis, not a deterministic technique. So in queuing analysis, we rely on the probability, on statistics, on average. Okay, so we cannot really determine how many people are really in there on that exact time. We can only determine how many people on average is there queuing in during that time, but we cannot determine how many people are really actually in there. Okay, hence this queuing analysis is more on probability or probabilistic, not deterministic. Also, queuing analysis depends on the queuing system type. It can be a single server, or it can also be a multi-server. When we say single server, meaning there is only one server attending the queue. When there is two or more, then that is considered multiple server system. In this video, we will focus our discussion on the single server system. We will have another discussion, another video for multi-server system. So let's illustrate. This is one cashier, and these are the people. This is the population waiting to be served. And since there is only one cashier, the people have to queue, have to fall in line to wait their turn to be served. Okay? So if there is a lot of people waiting to be served, there's only one cashier, then that could be problematic. Okay? Meanwhile, in a multi-server system, this is what happens. We have two or more servers. So these are the people, and there will be two queues, two lines. Assuming there's only a definite number of people waiting to be served, then that would be okay to have only one server, because anyway, when these people, since it's definite, the number of people is definite, then anyone would be served on their turn. But when there is an infinite population coming in and out, then having one server would be problematic, of course. Especially when you are in a mall. Imagine in a grocery, and then there's a lot of people coming in, there's a lot of people queuing in the line, falling in the line, and there's only one cashier. Imagine that. That could be exhaustive. The cashier can't attend to everyone waiting in the line, right? There has to be multiple servers. So these are the factors to consider when analyzing a queuing system. Number one, the queue discipline. In what order the customers are served. So it could be a first in, first out. So the first person who comes in the room or in the server would be served first, and the last person coming in would be the last person to be served. That's first in or first out. Or it could be giving them numbers. Okay, or it can be they will just sit and waiting to be served and they are called. So when we say queue discipline, this is the manner how the customers are being served. Okay? And another factor is the nature of the calling population. Where are the customers coming from? And usually when we say calling population, this should be infinite, meaning there is no limit. There is no limit to this number of people. We cannot ascertain how many people are really coming in that day. It could be 1,000, it could be 100, it could be more than 1,000. We do not know. It's infinite. For example, in a classroom scenario, the number of students coming into the class is finite. It's definite. It is the same. The number of students coming in on Monday would be the same number of students that would be coming in on Tuesday, Wednesdays, and so on, unless someone is absent. Okay, but it's finite. But under queuing analysis, we assume that the population coming in is infinite. And then the arrival rate. How often customers arrive at the queue? How many people, how many customers are coming into queue to fall in line? It could be 3 persons in 1 hour, or 5 persons in 1 hour, or more. Another, we have the service rate. How fast the customers are being served. It could be 2 people in 1 hour, or it could be 5 people in 1 hour. It depends. So, assumptions of the basic single server model. Number 1, again as I've said, there is an infinite calling population. There is unlimited number of people coming in from everywhere, from anywhere. Okay, we cannot ascertain how many people are there. Next, we have first come first serve queue discipline. So we assume that the first person coming into the queue will be the same person to be served. Hence, first come first serve, or first in first out. And third, there is a Poisson arrival rate. When we say Poisson arrival rate, this means that the arrival of one customer to another customer is independent from each other. Meaning they could arrive at the same time, they could arrive on themselves alone, and then when customers arrive at the same time are clearly negligible. And it could be averaged. Okay? So that's Poisson arrival rate. We can actually study the arrival using statistical tools. Okay? Next, we have exponential service times. When we say service times, this is the rate how the customers are being served, how fast the customers are being served. So when we say exponential service times, the service rate should be greater than the arrival rate. For example, if there are 2 persons arriving in 1 hour and the cashier or the server can only serve 1 person per hour, therefore the other person, the second person, has to wait for another hour. And we know in another hour, there will be 2 more people coming in and so on. And every person will be served for 1 hour. The service rate is very slow. And then the arrival rate is faster than the service rate. So the queue will just grow into infinite level. Okay, so we assume in this analysis, in a single server model, that the service rate is faster than the arrival rate. These are the helpful formulas in queuing analysis. Again, we'll discuss only the single server system. So keep in mind, however, that these formulas are applicable only to queuing systems having the foregoing conditions. Given that the lambda, or the arrival rate, this is the average number of arrivals per time period. This is the number of people coming in to the queue for every period of time. It could be 1 hour or minutes, okay, or in a day. And this is a mu. This mu is the service rate, meaning the average number of customers being served per time period. So again, when we say lambda, this is the number of people coming into the queue. While mu, this is the number of people, the average number of people being served in one particular period of time. And then the lambda is lesser than the mu, meaning customers are served at a faster rate than they arrived. The arrival rate must be lesser than the service rate, because when there is more people coming in than people being actually served, then again the queue will just go to infinite. So imagine if you can serve one person for 1 hour and there are 10 persons arriving in an hour. So meaning you have to serve 10 hours per 10 persons. In another hour there will be 10 and so imagine that. So the line will just, so this is our first formula. Take note of this. The probability that no customers are in the queuing system, either in the queue or being served, is computed as the P0 is equal to 1 minus lambda over mu. Again, this is the first formula in queuing analysis. The probability that there is no customers in the queuing system, either in the queue or being served, is computed as P0 is equal to 1 minus the lambda over mu. And the probability that n customers are in the queuing system is equal to lambda over mu to the power of n times the P0. Or it can also be lambda over mu to the power of n times 1 minus lambda over mu. Remember that this formula is actually for the calculation of P0. So it is just extended, okay? So to compute the probability that there is this certain number of customers in the queuing system, so that should be computed as lambda over mu to the power of n times the P0. Next, the average number of customers in the queuing system. This is the customers being served at the same time waiting in the line. So for example, there is only one cashier and there is one person being served and there are 4 other people waiting in the line. Therefore, there are 5 people in total in the queuing system. 4 are in the line and then 1 is being served. So 5 people are in the queuing system. So the formula to compute that is L is equal to lambda over mu minus lambda. Next, the average number of customers in the waiting line. So this is the people in the waiting line, not including that person being served. So that would be computed as lambda squared over mu times mu minus lambda. Okay, next we have the average time a customer spends in the total queuing system. So this is the number of minutes or hours that one customer spends from the waiting line down to being served. So this computed as W is equal to 1 over mu minus lambda. So next we have the average time a customer spends waiting in the queue to be served. So in our previous formula just a while ago, we have already mentioned the total time the customer wait to be in the waiting line down to being served. Then this formula is used to compute the average time the customers waiting in the line, not including those time being served. Okay? The formula is WQ is equal to lambda over mu multiplied by mu times lambda. Okay? Next, we have the probability that the server is busy. Example, the probability that a customer has to wait. This is also known as the utilization factor. So, it is U is equal to lambda over mu. Okay? And to compute the probability that the server is idle, our formula is I, meaning idle, is equal to 1 minus U. So this is the probability that the customer can just go in and be served right away. Okay? So let's have an example. For example, if the lambda is equal to 24 customers per hour arrive at checkout counter and the mu is equal to 30 customers per hour, meaning the lambda there are 24 customers arriving in 1 hour waiting to be served. But in the mu, the service rate is 30 customers per hour. So this is possible because, again, as I have said, the arrival rate should be lesser than the service rate. Otherwise, the population would go infinite. Then, the probability that no customers are in the queuing system, either in the queue or being served, is computed as P0 is equal to 1 minus lambda over mu. So that means 1 minus 24 over 30. So this means the probability of no customers in the system is 0.20. Okay? So there is a lot of chance that there is really a customer in the system. There is a little or minimal chance that there is no customer in the server or the system. Okay, there is a big chance, however, it is 80% chance that there is a customer waiting in the line. Next, the average number of customers in the queuing system. The customers being served and in the waiting line. So our formula would be L is equal to lambda over mu minus lambda. So we have 24 over 30 minus 24. So that means 24 over 6. So 24 divided by 6, there are 4 customers on average in the queuing system. Meaning, it is expected that if you have this kind of situation, there will be on average 4 persons in the queuing system. Maybe 1 being served and 3 in the waiting line, okay? Or maybe the 4 of them are in the waiting line and no one is being served. But on average, there are 4 people in the queuing system. Next, we have the average number of customers in the waiting line. So again, in our previous computation, that was the average number of customers in the queuing system, meaning being served and in the waiting line. But in this case, we are going to solve for the average number of customers in the waiting line itself and not including the one being served. So our formula would be the lambda, LQ is equal to lambda squared over mu times mu minus the lambda. So we have here 24 squared over 30 times 30 minus 24. LQ is equal to 576 over 30 minus 6. So our LQ, or the average number of customers in the waiting line, is 3.2 customers. That could be most likely 3 persons in the waiting line. Okay? Next, we have the average time a customer spends in the total queuing system, meaning from the moment he waits in the line to the down to the time that he is being served. So our solution would be W is equal to 1 over mu minus lambda. So we have 1 over 30 minus 24. So therefore, the average time that the customer spends in a queuing system is 0.167 hour or 10 minutes. That is 0.167 times 60 minutes. So this 10 minutes is the average time that the customer spends in the entire system, from waiting down to being served. Next, we have the average time a customer spends waiting in the queue to be served. Okay, so this is the time he is in the waiting line, waiting to be served. So our formula would be WQ is equal to lambda over mu times mu minus lambda. So 24 is over 30 times 30 minus 24. Therefore, the average time a customer spends waiting in the queue, not being served, okay, is 0.133 hours or 8 minutes. So that is 0.133 times 60 minutes, the average time the customer spends waiting in the queue. So therefore, if we will compare this 8 minutes to the previous one we have computed, the 10 minutes is the entire time the customer spends from waiting to being served. And we have here known that it will take 8 minutes that the customer has to wait in the queue or in the line. Therefore, 10 minutes is a total queuing time from waiting to being served, and 8 minutes is the waiting time alone. Therefore, it would take a server to serve a customer 2 minutes. It would take 2 minutes for a server to serve a customer. Next, the probability that the server is busy, the probability that a customer has to wait. This is known as the utilization factor. So it is computed as the lambda over mu. So 24 over 30. Then that is 80%. Take note that this utilization factor is the exact opposite of the P0 we have just computed a while ago. That was 1 minus lambda over mu. So here are the several important aspects in queuing analysis. First, the operating characteristics or averages. It is not exactly 4 people waiting in the queue or 1 person is being served or it will take 10 minutes. Again, those things we have computed are on average only, because queuing analysis is technically probabilistic and not deterministic. Another, we assume that there is a steady state averages, meaning the average today will be the same for tomorrow and for the next day and so on. We do not assume seasonal peaks or seasonal changes, for example during Christmas season. Another, related to this condition, is the fact that the utilization factor or the U must be less than 1. So again, in queuing analysis, we also assume that the U is lesser than 1 because the arrival rate is lesser than the service rate. Otherwise, again, when there are more people arriving than the service rate, then the management has to make another server to serve those excess customers. Okay? Hence, U is lesser than 1 and the lambda is lesser than the mu. So in other words, the ratio of the arrival rate to the service rate must be less than 1. The server must be able to serve customers faster than they come into the store in the long run, or the waiting line will grow to an infinite size and the system will never reach a steady state. Okay? So you try this. Try solving this problem and I want to know your answers. To determine the P0 or that the probability that there is no customer, also determine that there are 3 customers or the probability that there are 3 customers, and then the L, the LQ, the W, the WQ, and the U. So comment your answers down below and I want to know. I will check them if you got it right. Okay? Thank you so much for watching. Please watch also the other video we have for the multi-server system.